Going to look at process scheduling algorithm. Process scheduling. One of the major capabilities of the operating system is multi-programming. The objective of multi-programming is to have some process running at all time to maximize CPU utilization. Another capability of the operating system is time sharing. The objective of time sharing is to switch the CPU among processes so frequently that users can interact with each program while it is running. To meet these objectives, the process scheduler selects an available process, possibly from a set of several available processes for execution in the CPU. In order for this to happen, we have a process scheduler. For a single processor system, there will never be more than one running process. If there are more processes, the rest will have to wait until the CPU is free and can be rescheduled. Scheduling queues. We have different types of scheduling queues. The first is the job queue. As processes enter the system, they are put into a job queue, which consists of all processes in the system. We have the ready queue. The processes that are residing in main memory and are ready and waiting to execute are kept on a list called ready queue. The diagram illustrates how processes held in the ready queue are allocated to the CPU. In case we have a process P1 in the ready queue, it is allocated to the CPU. And there are three operations that can happen to process P1 once it has been allocated to the CPU. Process P1 can execute fully and it gets terminated or it gets ended. It can also happen that once process P1 has been allocated the CPU, a process P2, which is of higher priority, can make the partially executed process P1 to be swiped out of the CPU and taken back to the ready queue. Another operation that can happen to process P1 once it has been allocated the CPU, process P1 can be in need of an I/O device in order for it to complete its execution. Process P1 will therefore have to be swiped out of the CPU, taken to the I/O waiting queue in case there are other processes that are using the device that process P1 is waiting for. So once the I/O operation has been performed on process P1, process P1 will be taken back to the ready queue for it to await the CPU. A process scheduler schedules different processes to be assigned to the CPU based on particular scheduling algorithms. There are 6 popular process scheduling algorithms which we are going to discuss in this chapter. The first is the first come, first served scheduling algorithm. Next is shortest job next scheduling. Priority scheduling, shortest remaining time, round-robin scheduling, multi-level queues scheduling. So the diagram illustrates the different types of the scheduling algorithms. First come, first serve, priority scheduling, shortest remaining time, shortest job first, round-robin scheduling, multi-level queue scheduling. We are going to look at the first come, first serve scheduling algorithm. By far the simplest CPU scheduling algorithm, the process that requests the CPU first is allocated the CPU first. Just like in a bank, the first customer will be the first one to get served, and the rest will have to queue up behind the first customer. When a process enters the ready queue, its PCB or process control block is linked onto the tail of the queue. When the CPU is free, it is allocated to the process at the head of the queue. The running process is then removed from the queue. The diagram illustrates what usually happens to the queue. The queue has the front part and the rear part. The DQ operation happens to the front part. The NQ operation happens to the rear part. NQ is the operation for adding an element into the queue. DQ is the operation for removing an element. The average waiting time under first come, first serve policy, however, is often quite long. Consider the following set of processes that arrive at time 0. So we have process P1, P2, P3. Process P1 burst time is 24 milliseconds. Process P2 is 3 milliseconds. Process P3 takes 3 milliseconds. If the processes arrive in the order P1, P2, P3 and are served in the first come, first serve order, we get the result shown in the following Gantt chart. So, process P1 started executing at time 0. It takes 24 milliseconds for it to be executed in the CPU. Then process P2 is allocated the CPU. It takes 3 milliseconds to execute, ending at time 27 milliseconds. And then process P3 is allocated the CPU. It takes 3 milliseconds to execute and ends at time 30 milliseconds. So the waiting time for P1 is 0 milliseconds. Waiting time for P2 is 24 milliseconds. Waiting time for P3 is 27 milliseconds. Average waiting time for the processes will be 0 plus 24 plus 27 divided by 3, which gives us an average waiting time of 17 milliseconds. If the processes arrive in the order P2, P3, P1, however, the results will be shown in the following Gantt chart. So process P2 will start executing at time 0. It will take 3 milliseconds to execute. It ends at time 3 milliseconds. Process P3 is then allocated the CPU. It takes 3 milliseconds to execute and ends at time 6 milliseconds. And then the P1 process is allocated the CPU. It takes process P1 24 milliseconds to execute and it ends at time 30 milliseconds. Waiting time for P1 is 6 milliseconds. Waiting time for P2 is 0 milliseconds. Waiting time for P3 is 3 milliseconds. Average waiting time for the processes will be 6 plus 0 plus 3 divided by 3, which gives us an average waiting time of 3 milliseconds. This reduction is substantial. Thus, the average waiting time under an FCFS policy is generally not minimal and may vary substantially if the process's CPU burst times vary. The first come, first serve scheduling algorithm is non-preemptive, meaning it does not release the CPU willingly. Once the CPU has been allocated to a process, that process keeps the CPU until it releases the CPU either by terminating or by requesting I/O device. Disadvantages of first come, first serve scheduling algorithm is thus particularly troublesome for time-sharing systems, which it is important that each user get a share of the CPU at regular intervals. It will be disastrous to allow one process to keep the CPU for an extended period. So that's with the first come, first serve scheduling algorithms. In the next videos, we shall be looking at the other scheduling algorithm. Thank you so much for listening.